So now let's talk about the third definition. Now, let me introduce the concept of convergence in distribution. So the sequence xn converges in distribution to x, and we use the notation d with the right arrow, xn right arrow, and we write down the d above the right arrow and x if the limit of the capital Fxn x. So capital with subscript xn and x is the CDF of the sequence xn, and that limit is equal to the fx x, which is the f with the subscript x, and x is the CDF of x. So xn converges in distribution to x if the limit of the CDF of xn is the CDF of the x for all points x at which fx x is continuous. So here we consider the convergence in distribution for all points x at which the fx is continuous. So we consider the convergence in distribution for all points x where the CDF of the x is the continuous. And the capital F with subscript x is called the asymptotic CDF of the sequence of xn. So let me give an example related to this concept. So now I use x use x1 through xn. Now this is the not the sequence but the IID random samples. And let's consider the maximum statistic. So we have IID uniform between 0 and 1, and we consider the x subscript with parenthesis n, which is the maximum statistic of the xi's. Let's consider the absolute distance between maximum statistic and 1. And then this one. So if we decompose this the absolute value into this probability into two parts. So one part is the probability that the maximum statistic is greater or equal to 1 plus epsilon, and plus probability that maximum statistic is less than or equal to 1 minus epsilon. And then which is this probability that maximum statistic greater or equal to 1 plus epsilon is 0, because its maximum statistic is the maximum value that the take is the 1. So this the probability is equal to 0, and we have only probability that the xn maximum statistic less than or equal to 1 minus epsilon, and this probability is equal to this is the xi is less than or equal to 1 minus epsilon for all I. That probability is 1 minus epsilon power n. And then since the epsilon is the arbitrary value, in this case it cannot greater than 1. It's the arbitrary value, arbitrary positive value less than 1. So this, if you power n, and when n goes to infinity, that this value goes to 0 as n goes infinity. So you can see that the xn converges in probability to 1. Now let's look at the convergence in distribution. For the last example, let's take epsilon to t divided by n, and then you can see that probability xn less than or equal to 1 minus epsilon is equal to probability maximum statistic less than or equal to 1 minus t divided by n. So t is any positive number, and then this is equal to 1 minus t with n and power n, and then by the the calculus theory is going to be e to the minus t. So hence p probability that n 1 minus xn less than or equal to t is approach to 1 minus e to the minus t. So by rearranging terms, then you can see that the probability that the n times 1 minus xn less than or equal to t is approaching to 1 minus e to the minus t. And here means that, so this is the this is the CDF of the exponential distribution with lambda equal to 1. So we can see that, and we can say that n times 1 minus the x, the maximum statistic, and convergence in distribution to x, where x follows exponential distribution with parameter with 1. And then, so we have looked at the three concepts: the almost sure convergence, and convergence in probability, and convergence in distribution. So with between these three concepts, there are important relationships. So I will introduce two theorems, and I will skip the proof of these two theorems, so you can accept as a fact. So first theorem is, if xn converges almost surely to x, then xn converges in probability to x. So almost sure convergence is stronger than the convergence in probability. And the second part is, if xn converges in probability to x, then xn converges in distribution to x. So convergence in probability is stronger than convergence in distribution. And then by A, you can see that if xn converges almost surely to x, then xn converges in distribution to x. And another theorem is, so for constant c, xn converges in probability to C if and only if Xn converges in distribution to C. So for convergence to the constant, the convergence in probability and convergence in distribution, they are equivalent. So let's look at the example for this one. Now we have an xi, this IID with uniform 0 and 1, and we consider the maximum statistic of xi's, and let's say that's equal to yn. And then the goal is to find asymptotic distribution of the yn. So note that f of yn f of yn y is n times y power n minus 1. So this can be easily derived by using property of the maximum statistic. So that's the our PDF of yn. Then f of y and y So the CDF of yn takes the three values according to their range. Y is less than or equal to 0 is, in that case, the CDF of yn is 0. And if y is between 0 and 1, then CDF of yn is y power n. And that's from just integrating between 0 to y of the PDF. And then if y is greater or equal to 1, then clearly the CDF of yn is equal to 1. And if n goes to large, it's going to be 0 when y is less than 1, 1 if y is greater or equal to 1. So when the y is less than 1, then the CDF is approaching to 0. Then the y is greater or equal to 1. Then the CDF is the approaching to 1. Approaching to 1. Hence the yn convergent distribution to 1 and yn converges in probability to 1. So you can see that the yn converges in distribution to 1 and yn converges in probability to 1. Or you can use the result that we just described. So we show that yn converges in probability to 1. Then by the theorem, the previous theorem, so you can you can see that the yn converges in distribution to 1. So you can use either the just this previous theorem or previous theorem for just using this result or the previous results.